thank you. Thanks for sticking around and thanks for inviting me to give a talk. So, I'm a data scientist at Versal, and Versal, we are an online education platform. So we help teachers and content providers put together content so they can teach, engage, and give assessments. And get assessments from either students or employees or whoever wants to consume content. And what I want to talk to you about today is how we envision content, how we curate it, how we create it, and how we explore it. And especially for the exploration part, I want to talk about knowledge maps and how we create a knowledge map using taxonomies and how we balance between a generation of a taxonomy and a visual use of a taxonomy. So it's both informative but also useful. Okay, so first of all, content creation in the classroom. So when we speak to teachers, what we see that teachers are using now in classrooms is predominantly what we all know: PowerPoint, Word, a few Google products. But it doesn't really complete the cycle. Okay, so when a teacher wants to teach something, they have to put together content. So it's usually cutting and pasting content from around the web, if it's video, if it's text, if it's a few images. Okay, they have to distribute it to their students, so they have to send out a PowerPoint or present it. And then when you want to get an assessment back from a student, you have to submit the homework. Okay, so there are a bunch of online platforms that do that, but it's still kind of a broken process. The frustrating part of it is that we're now, with the current state of the web, we have some very beautiful websites. Is anyone familiar with Snowfall, a story from the New York Times, adventure up in the mountains? Beautiful media, a lot of different types of media blended together, beautiful visualization. Anyone read the 538 New York Times blog? No. Anyway, very beautiful data visualizations. So the whole idea about it is that we have a lot of really nice content, a lot of nice visualizations, but is it really for everyone? But it's really for everyone and has like a media team, a lot of good developers, but we want to be able to give that access to everyone else. So at Versal, what we're doing is we're creating tools to both curate and publish very beautiful visualizations and tools very quickly. And the idea behind it is we start off with very small components, with gadgets. So a gadget can be a piece of text, video, audio, drag and drop tools. We group these gadgets together to create courses. Teachers can publish them and share them. Okay, so very briefly, so we have a course about photosynthesis. We can take videos, mesh them up with text, add some Google Drive documents, Quizlet, all sorts of third parties, and even go very deep and very complicated, like making a time series of all sorts of events around the Civil War, annotate them with content. That's very easy. You can just drag and drop it. Okay. So why am I telling you all of this in this context? We have a lot of content. We deal with a lot of content. We want to help people organize all of this content. Okay? So you can take this content, regardless of Versal, and you can stick it into your own website. A gadget is an iframe, so you can put it into your blog, into your WordPress, whatever. So we deal with content all the time. So the question arises is, how can we give people access to a lot more of this information, and how can it be very useful for everyone, okay? And how do we present it in a way that's not too messy, both in a way that you can see a very large picture of all the content you want to look at, like a 20,000-foot view, and also like down to the very small details of the specific content that you want to capture. So what we're working on is called the Versal Knowledge Map, and try to think about it as a Google map for content. Let me demonstrate a little bit more. Okay? So the objective of the knowledge map is to allow people to both explore large amounts of content, exploit it, use it and extrapolate it, and then share it. Okay? So let me try see if we can get the knowledge map to work with a live demo. I'm gambling here. Live demos have a tendency to do these things. What's going on? Is this visible? Okay. So this is a knowledge map of chemistry. So what we've, wow, this is, all right. I'll go back to the, it's not really working the way I want it to. But the idea of the knowledge map is we can take a topic like chemistry or biology, computer science. We can break it down into a taxonomy. So if we look at chemistry, we started from a very broad view of, this is computer science. We can take a look at artificial intelligence, computer science, the broad topics within computer science, and then with each one of these topics we can drill down to it. So clicking on each one of these will drill down and expand more topics. Okay? Let me see if we can, I'll give a short demo of how we drill down. So for example, say organic chemistry, I can drill down into organic chemistry and get a breakdown into more precise things like organic compounds or heterocyclic compounds. So I can drill down into each one, and in this case what we've done is we've taken just the summary of Wikipedia pages in each node and displayed them as the usable bit of content. Okay? Now I can use this, I can create a reading list for myself, I can add it and email this to myself, or I can look at a larger view, like for example, if I want to see the context of a specific topic over all of the knowledge map, let's say like DNA, I can search for DNA and it will highlight DNA with contexts of all of the different branches within chemistry. So I can read up about all the different ways that DNA is mentioned. Okay, so I can summarize that and look at all of the different ways that DNA is mentioned in the knowledge map. Okay, so what I want to tell you about is how we're thinking about creating this knowledge map in a functional way. So you can browse it both to get that nice overview and drill down into the details. So what we've used to create the taxonomy is we're using Wikipedia as our source. So Wikipedia comes in a very nice structured way. Wikipedia provides us with the dump of all of the Wikipedia pages. So it's roughly like 40-something gigabytes in English, encompassing around 13.5 million documents. Within, and that's just the English language. Okay? And we can also get another set of relationships, which is the Wikipedia categories. Does everyone know what the Wikipedia categories are? Okay, so every page in Wikipedia can belong to one or many categories, and these are usually human-labeled categories. Lately, there are a lot of bots that do that as well, but you can group pages into categories that way. It goes into even more detail. You can have subcategories, and using that table, we can create part of what the taxonomy is. But when we started doing it that way, we looked at that big SQL table and we started creating a taxonomy, we very quickly ran into a few problems. Like it grows very wide, it grows very deep. A lot of the pages and categories that are automatically added on don't make too much sense, so we wanted to organize a lot of it. But we also wanted to organize it in a way that it could fit into a single page, that you can see it and you could read it and interact with it. Okay? So besides the parts that we can download from Wikipedia, like the categories and the pages themselves, there are a few very important parts of Wikipedia that help us with content curation. So the first part is the portals. Has anyone here looked at Wikipedia portals? Know what they are? No? I'll show you a snapshot of it in a moment. And then there are major topics. So each portal has a list of major topics in it, and those are the key concepts that the curators of that portal have deemed important for people to know about. Those are like the highlighted pages of that portal. And we use those as a positive control to know that we're making a taxonomy that is comprehensive. Okay? So that once we generate the taxonomy, each page of those major topics is in the taxonomy, or at least a subset or large subset of them. So we know that we have completeness. Okay. So categories, for example, can you see like the size of the text? I don't know if it's clear or not, but the categories, for example, in biology, we have a large number of categories. Each category has subcategories. Some categories do not have subcategories. And the topics, like I said, are just a list of specific pages that are pretty important by the community for that specific subject. For biology, for example, we have transcription, genetics, Mendelian genetics, and so on. These are very important concepts within each subfield. Okay? So when we create the taxonomy, I jumped around there, we start off with the root, which is, say, biology, and then we start off building off categories as children. Categories have children, which can be either another category, a subcategory, or a page. In this case, we call it a leaf. Okay? And if that leaf is one of the major topics, we label it as a topic, and we know that we have one of those inclusive sets. Okay? So very quickly, this taxonomy grows very big and wide and deep, so we want to be able to maintain it and manage it so we can actually browse it. So we had a few challenges over here. So first of all, we wanted to understand how deep we want to go. Okay? So we want to go deep enough so we capture all of the topics that we want, all of the important pages, but we didn't want to go too deep, otherwise we lose context. So for example, if we're in biology and we mark mufflers or transmissions, then we know that we've gone too far and that's just not related to biology anymore. Okay? Within the categories themselves, some of the categories will have child categories or subcategories that will reference the category itself, so we have a lot of feedback that goes on, a lot of circularity that goes on, so we want to eliminate that. A lot of the nodes can repeat themselves in different contexts, so in some cases we want that repetition, and in some cases we don't want that repetition. So for example, what I showed you before, we want to be able to capture DNA in all of its different subcategorization, but we don't want to replicate a node of, let's say, photosynthesis. Like we wouldn't want to capture photosynthesis in many different places as to take it out of context. Okay? And finally, the constraints around this are that we want to be able to visualize all of this. And the main part of the constraint is, can we read the labels on the text? Like, can we actually see this as a map? So when we look at a map, when you look at it far away, you see less details. You don't see the names of the roads or anything. But when you zoom in, you can very clearly see names of the roads, but you won't see the name of the city. So it's all about how do we manage that type of, the balance between resolution and the 20,000-foot view. So we came up with a few levels of, a few rules on how to include and exclude different branches. So we're calling it the depth versus breadth criteria. What we do over here is we establish a few rules that are based on the visualization criteria. Okay? So we take a look at how many nodes we have for each level. Okay? So let's say we have a subcategory that has only 2 or 3 nodes. That is not sufficient for us to make it a category. You go in there and it's very sparse. There's not much to look at. Okay? If there are, however, a lot of different nodes in that same category, we want to either split them up into other categories so that you're not overwhelmed with too much. So we cap that at a certain number. Okay? We also take a look at the number of children of each node. So if a category only has a single child, we will collapse that. We'll collapse that node and merge it with a different node or a different branch. Okay? And right? And finally, one of the rules that we use to generate the breadth versus depth is to see that if we've gone down a certain path deep enough to encounter one of the major topics, we'll stop the expansion of that branch at that point. Okay? If it has reached the maximum level of the maximum depth level that we want that taxonomy to have, we'll see how far away, like how many levels away are we from the next major topic. And if that major topic is not included in the rest of the tree, we will surface it up and include it into that subtopic. But if it's included in the tree, it will stop that expansion over there. Okay? So all of these rules we kind of summarized into 3 different operations that we're doing on the taxonomy. So first of all, we can remove leaves, topics, subcategories, and categories based on some semantic rules that we've devised. So basically, we look at the content of each page and determine its relevancy. So what we've seen going through a lot of Wikipedia pages is that there are a lot of geographical locations that don't make too much sense to add in. So we filter out geographic locations. Okay? Another type of item that comes up quite a bit is lists and lists of lists. And there's even a page called list of lists in Wikipedia, a very entertaining page. Okay? So we remove kind of those types of pages. Okay? Some of the other operations that we do is we collapse branches. So if there isn't enough information to merit a new split inside the taxonomy, we'll collapse the branch and try to merge it with another branch that we can enrich data upon. So that when you go into a certain node, it won't be with only like 1 page on it or 2 pages. Right? So we'll have there will be more richness inside. And we'll also split branches into several groups if we have, let's say, a node with 40 or 50 or 60 children. So that's just too much content on a page, and we'll try to split it in one way or another. Okay? All right. So one of the problems that we saw that came up pretty often was text collisions. So if we have a lot of nodes on the page, we have very large captions or titles, and they'll collide with other titles. So we're trying to get around that problem. So that was a kind of interesting problem to get around. We started playing around with kerning, with different ways to angle the text, different ways to size the text automatically based on the number of nodes, to select nodes based on the size of the text. But we did this for a while, and then we kind of discovered a very neat principle of working with taxonomies. And what we saw is that the deeper we go in the taxonomy, the titles of the text tends to be longer, okay? And so the more specific you are, the more words you need to describe that concept. And we saw this over several different taxonomies. So we've gone through computer science, biology, math, and chemistry, and this is and it reoccurs in all of them. So we can see that both on the names of the topics and on the names of the individual pages. So that kind of phenomena indicates to us that we're going in the kind of right direction. So we try to minimize the length. We try to go for nodes that have smaller text that are higher up in the hierarchy, and very long and much longer descriptions in the lower levels of the text. And it worked pretty well for both cases, and slowly we can eliminate a lot of those collisions. It's not perfect at this point, but we're still iterating through it. All right. So bringing it back together. So what we're doing with Versal is we're trying to create both immersive experiences with a lot of interactive tools. Okay? We're trying to take a lot of knowledge and let people share it and bring it in together. And finally, we're always facing with a challenge, right? We want to be able to always merge content with very interesting and fun visualizations. And that's what we're facing every day. Those are the challenges that we like handling, and also we're hiring to do exactly that. So if you're interested, let me know, and I'm open to answering questions. Thank you very much. I'll put the URL for the knowledge map. It hasn't been working on the presentation that much, but I'll post the URL in a moment.
So going over some of the heuristics you can use to build a knowledge graph, are you guys just using those heuristics, or do you have something else going on to help you build up all of this?
So what we're trying to, it's a balance between the visualization rules and the way that we can automate on generating the taxonomy. So when I say, it's kind of like an in-between between a heuristic and a cost function. So we can't really formalize the cost function that well around the taxonomy. So we are resulting to heuristics. And as we're going through different taxonomies, we're doing it as a heuristic until we have enough taxonomies that we can generalize it as a cost function. But the idea is to generate a cost function around it and to make it a more generative approach and not like a, yeah, I feel it kind of way.
How are you going to find out which category course?
So when we have courses, the gadgets that we use at Versal, they're annotated with text. Okay? So what we're doing at the moment is we're looking at matches between the text in the gadget, and we're finding the best matches between the Wikipedia taxonomy. When we have a good match, we can use a bunch of methods like TF-IDF or cosine distance. We can match the best pages on Wikipedia, and then from there we find the tags or the names of the Wikipedia pages that correspond best to that course. And then we can trace them up through the taxonomy to find the root, and from there we can label courses in a comprehensive way. And it depends. The way that we're doing it this way, instead of using like a topic model or a hidden model, is that we can control specifically the names of the tags that we want. So if we use LDA, for example, we get a vector of labels which may or may not make sense to people. Okay, so LDA can come up with a set of tags like beach, sandals, umbrella, watermelon, sand, banana. And that won't necessarily tell you too much about a course about beach volleyball, right? So we want the labels for these courses to come from a human readable way. And we thought Wikipedia was a good place to start.
So you could drill in pretty well. Do you have any way to go across and traverse the same levels? I mean, for example, if you've got natural language processing on there, you might want to be able to traverse across to AI or machine learning or science. You might want to be able to traverse across optimization, math, and be able to bring all that stuff together. Do you have any way to?
We're looking into that. We haven't found a good way to do that also on the visual part, because it will require transformation that doesn't have the same level across all fields. So, for example, if you're looking at so you're 3 levels deep, and you want to find an equivalent term for a similar topic in a different branch, it might not go that deep, or it might go way deeper. So that type of traversal doesn't have, for lack of a better word, a trajectory. Otherwise, it's just the same level that you're traversing. So it might not give you the same context. Does that answer your question? All right. Thank you very much.